projector. Hopefully it's on. And we'll go from current slide. Name, please. Huh?
J. Exari.
Okay. Okay, got it. Tyler. Name, please. Huh? Porterfield, got it. And get your name on the back. Jet. Okay. There it is. Sorry. I just missed it. Okay, anyone else come in since I called roll? Okay, this morning we got a whole slug of an iron. This is not good. Why is the projector not projecting? Did it do anything? Yes, there we go. Okay, don't know why. We got a whole slug of announcements. This is sort of the beginning of the year, flood of announcements. There are a few more that I read last night, but I wasn't on a printer, so I couldn't do this. But the first of these, I don't know if any of you know Mr. West, who teaches sociology and history. He's also our coach of the College Bowl, or Scholars Bowl. Okay? And they are organizing now. We are once again gearing up for Scholars Bowl, and I could use your help in getting out the word. He's writing this to us. I have attached a PDF flyer and also included a little paragraph below, blah, blah, blah. Okay. Lawson State Scholars Bowl is recruiting players for the 2019-20 season. Scholars Bowl is a competition of questions and answers played by teams with buzzers. Questions are read, and players buzz in without consulting when they think they know the answer. If they give the correct answer, they earn points, plus a bonus question in which they can work with their team to earn additional points. Questions cover a wide variety of academic topics, mostly from science, literature, history, fine arts, geography, philosophy, and the social sciences, plus pop culture, sports, and current events. Lawson State team practices weekly. That's with the EE, not WEA. No, never mind. Okay. And competes against other colleges 2 or 3 times each semester. The first practice and interest meeting is this Thursday, day after tomorrow, 12 o'clock noon, down in A261. That's down on the lower level of the second floor, about midway down on the left. For more information, please contact Mr. West. Okay? Here's a little flyer. Scholars Bowl is currently recruiting players with knowledge of any subject, including history, literature, science, music, current events, mythology, and mathematics. All right. Made it. Okay. So try to participate. It's a lot of fun, basically, is what it is. And I think you'll wind up learning a whole lot of stuff that may help you actually in classes. So I've had several people come in. You know, one of these is Lindsay, right? Yeah. Okay. And name, please? Second. Okay. Last name one more time. Jordan. Okay, got it. I can't hear well. You go by Katie? Yes, sir. Oh, okay. All right. That's part of what threw me. Okay. Did someone else come in since I called roll? Fairly recently? Not? Okay. Okay. Now, that's the Scholars Bowl. We also have a math team. The math team meeting is this Friday from 10 to 12 over on the Birmingham West Campus in the Science Building, room C103. That's a difference. I think they used to meet in C100, but they're in C103 this Friday, 10 to 12. Second. I got it. Thank you. All right, good deal. And that also is a lot of fun. You might think, but I've had a student before, I had him in a Calculus 1 class. And when we started doing Calculus 1, he was like a deer in the headlights, and he was fearful to answer questions. It's a small class, so I could tell he was not at all comfortable. But he joined the math team, and by the end of the term, he was a top student in the class. I mean, he got his confidence, he got to really enjoying it, and so it can really be helpful. So please consider it. Huh? Jeremiah. Why can I not find you? There you are. All right, good deal. Anyone else come in since I called you up? Okay, so that's Friday, Birmingham West Campus, 10 to 12. And while I'm on the subject of this coming Friday, let me make this personal announcement. Earlier, the end of last week, got an email saying I had a meeting at Shelton State on Monday. I thought, why do they have meetings on class days? And I was required to be there, blah, 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 okay? And then I found out yesterday they had the day of the week wrong. Now, I can see missing a date, but they had the day of the week wrong. It was a Friday, okay, this Friday. So I will not be on the Birmingham West Campus for office hours 8 to 12 this Friday. I'll be in Tuscaloosa at Shelton State. All right, now this, you have some time to deal with this one. This is the NASA Community College Aerospace Scholars Program, NCAS. There's great information here. I'm not going to read it all. And we've had several students from Lawson participate in this over the last several years, and they have had a great time doing it. You actually get to interact with some space missions, you know, and actually participate in some of the stuff that's going on those. It's an incredible program. I'll have the flyer up here. It has a bunch of websites you can go to. Most of them are go.nasa.gov, and then there's other things after that to take you to various places. So please, if you're at all interested or if you know of someone interested, spread the word. This is pretty, it's a great program. And then, this was in my mail this morning when I came in. It's from the Board of Governors of the Federal Reserve System. I went, am I in trouble? Okay. But it's the College Fed Challenge. You can actually compete with against other colleges to do policy recommendations on the Federal Open Market Committee. It's pretty incredible what you get to do. The winners get to meet with the Board of Governors and with the chair, Jerome Powell. It sounds incredible. And then also included in this is exploring careers in economics. If that's not an area that you thought you might be interested in, it's where my older brother ended up, and he loved it. Okay, so if you want to see any of that information, you certainly can take a look at that. Any questions before we get started on real math? Okay, sorry, all the announcements. All right, we're on page 44, chapter 1, which is functions in the graph, 1.4 functions. We're on the vocabulary, top of page 41, just 4 quick questions. Fill in the blanks, so let me know. Number 1, a relation that assigns to each element x from a set of inputs or blank. What's your set of inputs called? Second? Domain. Excellent. Exactly one element in y in the set of outputs, which is set of outputs, range, is a blank. Function. Excellent. Okay. A whole herd of people trying to get here in town to do the vocabulary. All right, let's see. Any of you Thai? Okay, Thai. Okay. Amari hasn't made it in yet. Jateria, not here yet. Sharona, got it. Cassidy, not here yet. Quan's not here yet. Richard's not here yet. Rachael, right? Okay, I can't ever get it pronounced right. Amber Pinkert's not here yet. Amon's not here yet. Amber Senior, not here yet. Charles, I'm here, but the other one's not. Mel's not here yet. And Kara, not here yet. All right, glad y'all are here. All right, number 2. We're doing the vocabulary, top of page 44 in the section 1.4. For an equation that represents y as a function of x, the set of all values taken on by the blank variable x is the domain. What do we call the variable x? 4th of July. Independent variable, very good, okay? And the set of all values taken on by the blank variable y is the range. Dependent, very good, okay? The 5th of July, no, I'm just kidding. Okay, number 3. If the domain of a function f is not given, then the set of values of the independent variable for which the expression is defined is the blank blank. Second?
Set of all real numbers.
No, just two words. I'll give you a hint on the last one. It was part of the first part of the question. If the domain of the function f is not given, then the set of values of the independent variable which the expression is defined is the blank blank. Second? Implied domain. Excellent, excellent, excellent. Number 4. One of the basic definitions in calculus uses the ratio f of x plus h minus f of x divided by h, as long as h isn't 0. This ratio is a blank blank. Both of them are math operations. Difference quotient. Excellent. Very good. All right. That finishes 1.4. 1.5, still in Chapter 1, Functions in the Graphs. 1.5 is analyzing the graphs of functions. And let me say this now. You'll see it repeatedly. This book loves graphs, okay? And they do show things that help you picture, visualize what's going on with functions, okay? And I hazard a guess, but I think that every quiz and every test you'll have in this class will have at least one graph. So if you have your favorite graph paper, plan to bring that or use it on the test and quiz. If you don't have any, I'll provide some. It won't be as pretty as yours, I bet, but it will be adequate. Okay, so we'll be analyzing the graphs of functions. One of the first things is using the vertical line test for functions. We've already talked about that one, right? Okay, we'll find the zeros of functions, okay? That'll be fun. We'll determine, in fact, that's the bulk of this section right here. Determine the intervals on which functions are increasing, decreasing, and determine relative maxima and relative minima of functions. We'll determine the average rate of change of a function, which sounds like a big new term, something you've already done, but with a different name. And we'll identify even and odd functions. All right, so let's look at the graph of a function. We've studied functions from an algebraic point of view. In this section, you'll study functions from a graphical perspective. Remember, many ways to express the functions. One, you can write sentences about them. Another is set of ordered pairs or tabular form, or written as equation, the algebraic one that we just were doing. Now we're going to do the last one, which is the graphical expression. The graph of a function f is a collection of ordered pairs, x, f of x, there they are, the same ordered pairs, such that x is in the domain of f, and then f of x would be, what is f of x, by the way? Y, that's in the range of f. As you study this section, remember that x is the directed distance from the y-axis, and y is the directed distance from the x-axis. So when they say directed, they mean if you're this side of the y-axis, that's a positive x. That side of the y-axis, you're a negative x. This side of the x-axis, positive x, y. That side of the x-axis, negative y. Okay, that's what directed distance meant. Okay, that makes sense. Y'all know that, right? Good deal. And this is how, they mentioned a couple of words before. I'm going to mention them again. This is a continuous function. Remember we had one time that showed a point here, a point there, a point there, a point there, and a point there. That was a discrete function, a finite number of ordered pairs. This is an infinite set of ordered pairs. It's a continuous function. If you went from here to there, how many points do you think are in between that? Just that little distance there, from here to there. How many points are in between that? An infinite number. You can't, in fact, you can't get from here to there without doing an infinite number. It's just incredible. The number line is infinite between 0 and 1. It's infinite going that way, this way. Infinite on the microscopic scale and on the macroscopic scale. This is a continuous function. You cannot list all the ordered pairs. They picked one, x, f of x, right there, okay? But every one of these is a different x with sometimes a different f of x, okay? So that's how a continuous function looks on a graph. Now, here's example 1, bottom of page 49. Here's a graph right here, okay? Use the graph of this function f, shown here in this figure, 134, to find first the domain of f. What you reckon the domain of f is? Now let me go back a slide. I was starting to say it before, but I didn't know this was coming up this soon. This, since there's nothing at the end here, this indicates that goes on and on and on. So without anything to tell you otherwise, you assume this domain starts at negative infinity, and since there's nothing at the end here, that it continues to positive infinity. That's the assumption. Okay? When you see a graph like this, which has a definite endpoint, you can tell, and this has a definite endpoint, or not, okay? This is not an infinite, well, it's infinite between here, but it's not infinite in the plus and minus direction. So what's the domain of this function? Yeah. What would be the domain? Okay, excellent. Okay, starts at -1 and it goes to 5. I need to see how you're saying that, okay? I hear what you're saying, but I can't quite tell if you do it. There are two ways we can express that domain. One is set notation. Let me get my pen set up. Okay? Which you prefer, set or interval? I don't care too much. Interval, okay? How would you start that to describe the domain here? Really? Oh, good guess. Okay, no, two choices, okay. It's a bracket Y. It includes the endpoint. That point right there at -1, 1 is included. That's why it's darkened in. So this would be a bracket. And what do you put next? -1. What do you put next? Simple little comma. 5. That was correct. Here's why I had to see what you're saying, not just hear what you're saying. What do I put next? Ah, there you put the open parentheses. Why? 5 is not included. Can you give me the last number that is included? 4.9999999999999999999. You can't give it to me because there's an infinite number of points between 4.9 and 5. And you can't tell me it's an infinite number. There's no end to them. So, but it doesn't include 5. Okay, so you got it right. Okay? Now, someone tell me the function values f of negative 1. Anyone do that? F of negative 1. Anyone remind me what f is? Y. Okay, yeah, okay. Now, and what's the negative 1 in that? What does that represent? Say again? The y is what? Okay, I think you're saying it right, but I can't make it up. When y is negative 1. Okay, when the y is negative 1? Not quite. What goes in the parentheses? Alpha of x. X is what goes in here. So what's your negative 1? The x value. So you go on the x-axis, go over here. The sharp. Yeah. Okay. Okay. So we go over here and find negative 1 on x. Look for the function. There it is. And what's the functional value there? 1. The y value is 1. Okay? If negative 1's x, positive 1's y. Okay, how about f of 2? What would that be? Negative 3. You got it. They drew it in there for you. Okay, what you do, you know when you see f of, what's in here is your x, your input, 2. So go on the x-axis over here to 2. Look up and down till you find the, there it is. There's a function down there. And what's the y value there? Negative 3. Perfect. Okay, what's the range of f? I'm going to do interval notation again. Up to you. Range of f. Interval notation or not? Interval. So how do we start? A little louder? Bracket. And where do we begin? Range. Say again? I heard something. Negative 3. Excellent. Okay. What do I put next? Comma. Positive 3. Perfect. Then bracket again. Excellent. Way to go. Because it doesn't get any lower than negative 3, it doesn't get any higher than positive 3, but both negative 3 and positive 3 are included in the range. So that's why the brackets are there. Does that make sense? Any questions? All right. Let's see how they did it. The closed dot at negative 1, well, you can't see it now, at negative 1, 1 indicates x equal negative 1 is in the domain of f, whereas the open dot at 5, 2 indicates that x equal 5 is not in the domain, so therefore it would be from negative 1, bracket negative 1, comma, 5 parentheses. That's the domain of f. Y'all were perfect with a little coaching. Okay. Because negative 1, 1 is a point on the graph, it follows that when f is minus 1, the y is 1. The f of negative 1 is 1. Okay? Similarly, because the 2 negative 3 is a point on the graph, follows that f of 2 has to be negative 3. There's the x value, there's the y value. xy. Okay. I'm sorry. Blocking the way. All right. And then, because the graph does not extend below f of 2, which is negative 3, or above f of 0, which is 3, the range is the interval from negative 3 to 3. All right. I can't remember if I gave this illustration to you before. I don't know if I find it helpful, but sometimes it's how I think of domain and range. I imagine that if I had a very bright light and put it way up high and maybe way down low as well, and then look for the shadow of the graph on the x-axis, that gives me the domain. and I'd have a dark shadow here because that would block it. All this would block it here, and this would be blocked here. But then here, you would have light coming through because there's no point there. So it's the shadow of the function from either direction on the x-axis. Same thing with the range, shine a very bright light over here and or over here, and then what portion of the y-axis is darkened? Well, from -3, that's darkened from this direction, up to +3, which is right there, darkened because it's there. Nothing beyond the light comes through there, so it'd be -3 to 3. That's sort of my dumb way of looking at it, but that's domain and range, one way of looking at that. All right. Any questions on that? All right, continuing with the graph. Oh, and by the way, for just about every exercise and example in the book, there is a checkpoint. Great things to do as soon as you get out of class. Okay? Now, the use of dots, open or closed, at the extreme left and right points of a graph indicates that the graph does not extend beyond those points. That dot here indicates, and the line doesn't go through the dot, indicates it stops right there. This one, open circle here, with no line on the other side of it, indicates it stops before it gets right there, right near it, okay? Open parentheses, okay? If, however, this line continued through the dot, like it continues through that one, then that would be with no dot at the end, and this same thing here, then you assume that it's going infinitely in both directions. If such dots are not on the graph, then assume that the graph extends beyond those points, and unless there's something to tell you otherwise, infinitely beyond those points. Okay. By the definition of a function, what is it? How many y values can you have for a given x value? One and only one. Okay, that means that the graph of a function cannot have two or more different points for the same x coordinate, because the x represents an x value, an input value, and if you can't have but one y, if you drew a line through that x value, it can only intersect that graph once. Cannot have two or more different points with the same x coordinate, and no 2 points on the graph of the function can be vertically above or below each other. It follows then that a vertical line can intersect the graph of a function at most one time. It may not intersect at all, but it can't intersect more than once. That observation provides a convenient visual test called the vertical line test for functions. Okay? Here's what it is. A set of points on a coordinate plane is the graph of y as a function of x if and only if no vertical line intersects the graph more than one time. Okay? You may not intersect at all, but if it intersects, it can only intersect once. Now, they go right on the zeros of the function without doing anything about example 2. And I'll ask you to pull out your books. If you don't have a book, I'll hold this one up here. Sorry, folks, not here. You should be here. Okay, but here it is. Here's a nice-looking parabola lying down there. Is that a function? No. Okay, here it intersects only once, but there, from there on to the right, intersects multiple times. Now, here's one that goes up and down, up and down. Is that a function? Yes, it is, because no vertical line intersects more than once. How about this one? Is that a function? Oh, why not? Say again? Okay, but that's not an issue, is it? As long as no vertical line intersects more than once. That one doesn't intersect at all, but that's not more than once. Every other vertical line that hits those two lines intersects only once. Those in the middle don't intersect at all, but that's okay. Just like vertical lines over here don't intersect. Okay? So that wasn't a function either. Okay. So the first was not a function, the other two are. There is a checkpoint at the bottom you can probably do immediately. Okay. So let's move on. Any questions on vertical line test? Very handy visual tool. Tell whether it's a zero of a function or not. I mean, whether it's a graph is a function or not. So let's move on to zeros of a function. We actually did some of this in the section 1.4. 1.4 introduces to a lot of stuff. That's why it's so long. But if the graph of a function, but now we're looking at graphs, not the equation part, but the graph part. The graph of a function of x has an x-intercept at a0. Okay? What was the f of x? Y. What's your y here? 0. Then we call that a 0 of the function. If the y value is 0, then that's called the 0 of the function. Not the x value, okay? If the y value is also called an x-intercept. Now, how many x-intercepts can you have? Say again? No, you can have as many as you want. Remember, x-intercept, it can be breaking the x-axis many times. Y-intercepts, how many can you have? No more than one, right? No more than one. You may not have any, but you definitely can't have more than one. But you could have more than one x-intercept. Every one of those would be a 0 of the function. So 0 of the function of f are the x values for which f of x equals 0. We said that in the last time. Now with the graph, those are your x-intercepts where it crosses the x-axis. Those are your zeros. We also sometimes call them the solutions of the function. Okay? So, what we need to do is find the zeros of each function. How will we do this? A. Let's just deal with A first. Second? Set it equal to 0. 3x squared plus x minus 10 equals 0. We set the function equal to 0. The y equals 0. And that will give us the zeros of the function. Now, how are you going to solve that? Got two choices. And I'm all right. Got it. I think I asked y'all this before. What's your F word? Ah, yes. Why don't we do that? Okay? If it's factorable, we don't know if it is. It may not be. If it's not factorable, what do we use? Anyone know? Quadratic formula. Perfect. Let's try factoring. I call it unfoiling. Okay? Foiling, you start with the first. So unfoiling, we start with the first. What's the only factorization of 3x squared? 3x times x. Perfect. So that'd be 3x here and x there. Okay? Then we go to, not the outer, but the last. And look at the sign of the last term. Okay? What is it? Negative. What does that tell you about these two signs? They've got to be different. But we don't know which goes where. So we make a guess. How do you want to do it? Plus minus or minus plus? I don't care. Minus plus. Y'all are looking ahead, aren't you? Okay? Now, we come to, what's the possible factorization of 10? And you got several of them. 5 and 2 in that order? Let's try it. 5 and 2. Now, at this point, that's the trial. Now we see if we made an error or not. We check it. And we check it by foiling. 3x times x is 3x squared. We knew that one's going to be right. Then we do the outer, which is plus 6x plus the inner minus 5x. And what's plus 6x minus 5x? Plus x. Y'all were looking ahead, weren't you? Okay. Y'all can't be that good, okay? And then the last is minus 10. Perfect. So we did factor it right. That's why we got a smiley face. So let's erase the smiley face and get on to business. Okay? All right. What does that tell us, though? That just gets it factored. We have to do something with that. Say again? Set each of those equal to 0. Why? Because the only way you can get a product of two entities to be 0 if one or the other, or both, happens to be 0. So either 3x minus 5 is equal to 0, which leads us to think, well, that's the other one, or x plus 2 is equal to 0. What does that first one tell us? What would we do for that? We're trying to solve for x. Add 5. Add 5 to both sides. And divide by 3, so you get 3x equal 5. Divide by 3, and that gives you x equal 5/3, one of our favorite numbers of all time. And then the other one, subtract 2 from both sides, and that gives us x equal -2. Okay? Now, come back. Okay. Now, I like to check, because I don't like to make errors, okay? I make plenty of them, but I don't like to. So let's try these. 5/3. What's 5/3 squared? Anybody know? Pretty early in the morning for this. What is it? A little louder.
1.6 repeating. 1.6 repeating.
Wow, look at that. She's already got it in the decimal. Okay. 5/3. It's 25/9, right? Squaring this, 25/9, right? Okay. 3 times 25/9 is 3 goes in the 9. 3 times, so that would be 25/3, right? So that's 25/3 plus 5/3. How many would that be? 25/3 plus 5/3. 30/3, which is 10 minus 10 is 0. Yes, it works. Okay. How about -2? Let's try that. -2 squared is?
4.
Times 3 is?
12.
12 plus 2 is? I'm sorry, minus 2 is?
10.
10 minus 10 is 0. Yes, that works also. Okay. So we found our 2 zeros. The other way we could have done it was graph the function. I prefer algebra. Graph the function, find the 2 places where it crosses the x-axis. I could probably pick that one out pretty easily, but this one I'd say, where is that exactly? Because it'd be in between the tick marks, and it would be hard to figure. All right, find the zeros of B here. I'm going to erase part of this that snuck over into B's territory here. We got our answers. Okay. All right. Okay. Find the zeros of that function. Oh my word, how are we going to do that? What would be your guess? Say again? Set it equal to 0. So we'll say the square root of 10 minus x squared is equal to 0. Okay, please come back. No, not there. What's that? Yeah, well, I'm not paying attention. Okay. All right. Sorry about that. I don't know if I have a bad connection down here or... Yeah, I shouldn't have touched it. Where's my sledgehammer? Okay. It's something about... When I jiggle the screen, let me see. Okay. All right. Now, there's a couple ways you can do this. How would you proceed with this one? Say again? Square both sides of the equation. Okay, that's okay. When you square a square root, what do you get? You lose the square root. So it's 10 minus x squared. And when you square 0, what do you get? 0. Okay? Now, that's one way to look at it, and that's perfectly fine, if you can see it. The other way is the only way that the square root of this thing can be 0 if what's inside here is 0, which is exactly what this says. So it gives you the same thing. Okay, now what do we do? Add x squared to both sides. Okay, that gives us what? 10 is equal to x squared. Now, okay, and square root of both sides. I'm going to flip sides too. X then would be equal to, say again? Square root of 10, is that what I heard? Is that all? Plus or minus, anytime you take the square root of both sides of an equation, you have to include a plus or minus sign. Come on back, baby.
Anytime, no matter what.
What's that?
So that
Anytime you take the square root of both sides of the equation, you've got to include a plus or minus. I was going to say this when I can get this back. Okay, let me try this. Okay, it's not that side. There we go. The other thing I was going to warn about, anytime you square both sides of an equation, most of the time when you square both sides, you have to always check your answers because you may have introduced what they call an extraneous root. We're going to get to those later, but since this was 0, it's not going to give you any extraneous root. That's still 0. Okay, so, and when you take the square root of both sides, you have to include a plus or minus sign. Now that's if your problem makes sense with that. If you were trying to find the radius of a sphere, you wouldn't take the minus sign, would you? Because the radius can't ever be negative. So I don't want to say every time, but every time that makes sense. That there's not any reason not to. Okay, and find the zeros of h. What would that be? And by the way, if we were to graph that function, I can tell you how that one looks. This is the top half of a semicircle. And the zeros are at minus root 10 and positive root 10. Okay? We'll see that later. Okay, H. As an Irish quantum mechanics professor I had called it H. And I thought for the first several weeks of the term, what is this guy talking about? But it was always H. So H of t, no, H of t. When is that equal to 0? What would we do? Set it equal to 0. I'll just do it this way because I have room. Okay? Now what would you do? Okay, multiply both sides by t plus 5. Okay? And here the t plus 5s go away because one's in the numerator and one's in the denominator. Here, what happens on the right-hand side? Still 0. So you get 2t minus 3 is equal to 0. Okay? Come on back. There we go. Now what? Add 3 to both sides. Okay? And that gives us 2t is equal to 3. And then do what? Divide by 2. And that gives you t is equal to 3 halves. Now, that's one way to do that. Here's the other way, and this is how I usually think of it. Okay? If I see a rational form here, that's a ratio of two things. The only way that ratio can be 0 if that numerator can be 0. So I just, rather than multiplying both sides, I just say that has to be 0. Okay? Does the same thing. Gets there the same way, but there's no way. And frankly, with a problem like this, I also, before I wiped out the t plus 5, when I first looked at that, everything in, well, not everything, but, you know, I wanted to say to you and the others, but the book didn't, I want to put comma, t cannot equal what?
0.
Say again?
0.
No, t could be 0, no problem there. Say again? T plus 5 cannot equal 0. That's certainly true. T plus 5 cannot equal 0. And then solve that inequality. Yes, t cannot be negative 5. I like to write that down because you know it can. Okay. All right. Now, then when you get your answer down here, as long as that's not negative 5, that's your answer. Okay. Also, when we were here, I wanted to limit my domain here. See, this is a limit on your domain, implied domain. This one, too, has a limit. We didn't have to get into it, but it has to be between negative 10 and negative root 10 and positive root 10. If we work that out, we'd see that. It can't be out here, it can't be here, because if x was greater here or less here, then this thing would be negative. You can't have a negative there. So it has to be in between minus root 10 and positive root 10. And that you can see from your graph there. Okay, so let me clear my scratch. Are there any questions before I clear my scratch? Okay. I'll try to use a button when I can so that doesn't wiggle the screen. So let's do this. To find the zeros of a function, set the function equal to 0, solve for the independent variable, in this case x. Set that equals 0, and what's that way to solve it? Factor it. Okay. And you factor that, and they just popped it right up there, and that's where y'all were looking, weren't you? Never mind. I won't ask that question. Ask me no questions. I'll tell you no. I won't go into that. Okay. And then you set each of those equal to 0, and that gives you either 5/3 for one or -2 for the other. So those are the two places where that function has zeros. Here is the descriptor here. This is a parabola because it's a quadratic function. Maximum exponent is 2. It's something upward because the leading coefficient is positive. I don't know if you've had this before, but if you haven't, we're going to get to it later. And parabolae either are going to have two solutions, two x-intercepts, two zeros. They may have one or they may have none. And let's go over how that could be. If you were to raise this sum, like add 10 to that, and get this to move up 10 units, then only this point right down here would be touching the x-axis. Then it would only have 1 0. Okay. If you put it 11 or more units, or 10.1 or 10.01, then you raise it up until it doesn't quite touch the x-axis. Then you have no zeros. So you can have either 2, 1, or 0. Anything up to your maximum exponent, 2. Okay, and there are the two zeros. -2, that's pretty easy to pick up. This one, 5/3, that's 2, 1 2/3, somewhere over here. There it is. Okay. The second one, set g equal to 0, square both sides. That's what y'all said. Y'all reading the book, weren't you? Okay. And then add x squared to both sides, take the square root, but when you take the square root, you have to put a plus or minus with the numerical part. And that gives you that, and the zeros of that function, this would be a semicircle. This goes out to minus root 10 here, minus root 10, plus root 10 here, also to plus root 10 up here. Same distance because that's a semicircle. It's something just a little past 3, because square root of 9 would be 3, square root of 10 will be 3 point something, so it's just beyond 3. Just beyond -3 here and 3 there. Okay? There's your zeros of that. Now, if I drew the entire circle here, what would be the zeros for that function? Trick question. Say again? Okay. Trick question. Say again?
There's no negatives in a circle, so.
No, a circle, yeah, could have a negative in it. But guess what that circle would not be? It wouldn't be a function, would it? Because the vertical line test failed. That was a trick question. Okay. It wouldn't be a function. I said, what would be the zeros of that function? It wouldn't be a function if it was a complete zero, because it would fail the vertical line test. Okay. Mean. Okay. And then this last one. So h of t equal to 0. And they do the same thing y'all did, multiply both sides by t plus 5. What I basically do is say, only way this rational form can be 0 is that numerator is 0. So I just set that. I would also say t can't equal -5. Okay? Then solve that, and you get t equal 3/2. And that's a rational function that looks like that. That's just part of the graph of this function. Okay? The reason I say that, and we'll get to this later, like in 1.6, I think it is. No, 2.6. when we get there, we will find out this has another half to it, and that half would be up here, doing something like this. But it has no zeros because it's all above the x-axis. So that's the only zero for that one. Okay. And I wanted to point out to you, remember when I said, or you said, t cannot equal -5? Look at this. It's going down, down, down. Never reaches -5. Just keeps going down. We call -5, this is for later, a vertical asymptote. Never reaches it. Okay? Never crosses it. Can't touch it. Okay? It just keeps going south. Never reaches -5. And that's why I said over here, you'll have one that never reaches -5 from this side, but it's going to positive infinity, and then it goes like this. Doesn't reach the x-axis, so there is no other zero. We'll get there later. All right, that was zeros of a function. Guess what? There's a checkpoint. Please do those as soon as you can. And then, now we'll go to increasing and decreasing functions. You know what? This is where graphing comes in really handy, because it's easy to see on a graph when a function is increasing and when it's decreasing, okay? And that's what we'll count on. The more you know about the graph of a function, the more you know about the function itself. Consider the graph shown here. We don't know what function this is, but we can tell when you're going from -2, okay, you always refer to where the input is going. The input is the x value. When you go from -2 to 0, that function is decreasing. The function's decreasing. You're increasing going here, but that's not what you're talking about. What's the function doing when you go from -2 to 0? It's decreasing. And you always have your x going from left to right, left to right. X is always increasing. What's the function doing there? It's decreasing. How about when you go from 0 to 2? Constant. It doesn't change. It's 1 every place in between 0 and 2. And what's it doing when you're going from 2 to 4? Increasing. Now, why did I have to? I was going to say from 2 on. No, you can't say from 2 on, because this is a dot here, nothing beyond that. That means the domain ends at 4. So the total domain of this function is -2 to 4. The range of that function is 1 to 4. Perfect. Okay. And then you break the domain into the intervals, and that's where you talk about increasing and decreasing. From the interval from -2 to 0, it's decreasing. From the interval from 0 to 2, it's constant. An interval from 2 to 4 is increasing. Okay. Now, use words like falls or rises. The better thing is increasing or decreasing. It's okay to use those other terms, but constant is constant. There's not much you can do with that. Doesn't change, I guess you could say that. Any questions on that? All right, so here is our sort of definitions of it. A function f is increasing in an interval. Okay, an interval is some subset usually of the domain. In an interval, continuous interval, when for any x1 and x2 that are in that interval, as long as x1 is less than x2, x1 is always to the left of x2, if that's the case, this implies, if it's an increasing function, that f of x1 of the lesser interval of the lesser value here is going, if it's an increasing function, f of x2 has to be greater than that, so f of x1 less than f of x2. That's what it means for it to be increasing. Now notice there's no equal sign there, it's less than f of x1. But if the function is decreasing on an interval, when for any x1 and x2 in that interval, then f of x1 is going to be what? If x1 is less than x2, f of x1 will be greater than f of x2 because the function is decreasing on that interval. Okay? And the function is constant on the interval if for any x1 and x2 on the interval, no matter which one is less than the other, f1 of x1 is always equal to f of x2 for any two values on that interval. If they're always equal, that's a constant function on that interval. Make sense? Okay. A lot of blah, blah, blah for pretty simple concept. Okay. Let's talk about these three. Use the graph to describe the increasing, decreasing, or constant behavior of each function. Number A, what can you tell me about that?
It's increasing.
Everywhere. From minus infinity to positive infinity. Why do I say that? There's no dots here at the end. So we assume all the way. Now this is a cubic function, and anyone, now, you might question yourself here and say, what about near zero? That looks awfully flat there, doesn't it? Well, pick a value near zero, like negative 0.1. Okay? Cube that, and you get negative 0.001, but it's still negative. It's not zero. So it's not constant there. It's slightly increasing, very slightly. And then for positive 0.1, same place. Okay? So that is increasing everywhere. Now here's another cubic function, but this one has a linear term in it. This is not quite going to act the same. What can you tell me about the increasing, decreasing, or constant behavior of that function? Okay, and tell me where. See, I told you this one. I said from negative infinity to positive infinity. That was easy. How about this one? Okay, it's doing what? Increasing from negative infinity to negative 1. Then it's decreasing from negative 1 to 1. Perfect. And then it's increasing again from 1 to infinity. You got it. Notice you give the intervals on the x values, and the increasing, decreasing describes what the y is doing. Okay, how about the c? Here they give the function. This is called a piecewise defined function. Remember, we had those before. When x is less than 0, this is how you define it. When x is between 0 and 2, this is how you define it. When x is greater than 2, this is how you define it. Okay? So what can you tell me about that?
Infinity, negative infinity to 0 is increasing.
Increasing.
Then 0 to 2 is constant.
Constant.
Then 2 to infinity is decreasing.
Perfect. Very good. Does everybody see that? Okay. Now, let's see how they write it. This one, first one, the function increasing over the entire real line. They don't say real number line, but that's what they mean. Okay, the second one, the function is increasing. Now, notice how they put the intervals here. It's not a big deal, but it is how you're supposed to do it. Notice they don't put brackets anywhere. When you're talking about an interval, just include parentheses. Okay? Whether you include this endpoint or not, how can you tell? Is it negative 1 included here or there? You can't really tell. So just put a parenthesis. Not going to be wrong if you don't, but it's just a little more correct if you don't. So that was increasing from negative infinity to negative 1, just like you said. Decreasing from negative 1 to 1. Increasing again from 1 to positive infinity. Perfect. Okay, and this last one, increasing from negative infinity to 0. That is always a parenthesis. Constant on the interval 0 to 2, and then decreasing again from 2 to positive infinity. Any questions on that? Make sense? Okay. Then I'll leave it a little longer. Okay. Okay, everybody got it? All right. To help you decide whether a function is increasing, decreasing, or constant on an interval, you can evaluate the function at several values of x. But if it's a continuous function, you can't evaluate it everywhere because there's an infinite number of points when you need 2 points. Okay. However, you need calculus to determine for certain the intervals on which a function is increasing, decreasing, or constant. Hopefully, you'll hang around for that, won't you? Please? Yes. Good deal. Okay. Good stuff, Maynard. Okay. The points at which a function changes its increasing, decreasing, or constant behavior are also helpful in determining the relative maximum or the relative minimum values of the function. So here's the definition of what we mean by that. A function f of a is called a relative minimum of f when there exists an interval x1 to x2, that's on the somewhere in your domain from x1 to x2, that contains a. A has to be in between x1 and x2, somewhere in there. Okay? When there exists an interval for which, and the x1 is less than x2, that's why they put it first, okay? And it's less than x, and it's also less than a. And this implies that f of a, for whatever x you find in between x1 and x2, that f of a is always less than that f of x, except when x is equal to a. Okay? That means a is the very smallest value it can take on in that interval. That's why we call it a relative minimum. Okay, relative maximum, then the f of a is a relative maximum. Notice it's the function f of a is called the maximum. When there exists an interval x1 to x2 that contains a, and as long as x is somewhere between x1 and x2, then f of a is always greater than or equal to f of x. That means because a could be x, and in that case they'll be equal to each other. And it could be you have more than one maximum, okay? If all those values were equal, then they're all relative maximum, okay? And that constant function, every point on there is either relative max or min, depending on which way the function's going. Okay. So, this figure shows several different examples of relative maximum and minimum. Okay. What is that first point there? Relative minimum is the least value y that is taken on anywhere in that range of x. How about this one? Say again? That, yeah. Relative maximum, because it's greater than or equal to any of the y values around it. How about this one? Minimum again, because it's less than any of the others around, and this, of course, would be a relative max, because it's greater than all the other values around it. As long as you stay close enough. Now, why do we say relative minimum or maximum? This isn't an absolute minimum. That one's less. This is an absolute maximum. That one's greater. In fact, if this function keeps going like this, none of these would be an absolute maximum. If this one keeps going down like this, none of these would be an absolute maximum, minimum. But they would be relative, because in that little area around them, they're the lowest values. Little area around those are the highest values. That's why we use it relative. Okay, bless you. You'll study a technique for finding the exact point at which a second-degree polynomial, what do we call a second-degree polynomial? Had a sort of special name, we use it today. Quadratic, okay, a quadratic polynomial or second-degree polynomial function has a relative minimum or relative maximum. We'll do that later. That will be in Chapter 2. For the time being, however, you'll use the graphing utility to find the reasonable approximations of those points. And if you have a really fancy graphing utility, as in a graphing calculator, you can find really close approximations to those. Okay, so that was, what was the last? Example 4. We did not do example 5, and they're moving on to average rate of change. So I've got to go back and find, okay, this is probably going to be our best place to do. And this one they said use a graphing utility. I don't have one. If you have one, you can certainly use it. To approximate the relative minimum of this function. F of x is equal to 3x squared minus 4x minus 2. Okay? Now, I have a feeling by the way they asked the question that this probably isn't factorable. But you could use the quadratic formula. Okay? And since you could, let's do, because we haven't used that lately, have we? All right, let's do. What would be the quadratic formula for this? X is equal to, someone said something, minus b plus or minus the square root of, b squared minus 4ac. Y'all are close. But close only works in horseshoes and hand grenades. Never mind, we won't go there. All over, say again, 2a. Don't forget that, okay? There's your quadratic formula. I'm glad we brought it up. Of course, it erased, so there we go. Come back. Okay. Now, what in the world is our a, b, and c? A is equal to 3. B is equal to negative 4. And C is equal to negative 2. Now, I wasn't supposed to show you this here, but we will, okay? I don't mind breaking rules too badly, as long as they're not math rules. Well, I want that to come back to life. Come on back here. Don't damage my screen. Here we go. No, we don't. Okay. There we go. So let's plug in our values. What would that be? Anybody? A negative 4, which would be 4 plus or minus the square root of, which is 16 minus 4 times 3 times negative 2 all over 2 times 3. Perfect. Okay? Now, that will be 4 plus or minus the square root of what? 40, you said? Oh boy, he's already done it. See, this multiplies to be, okay, so that's a 40, is what you said, right? Divided by 6. Now, I hate to be too unimpressed with that, which I am impressed. I definitely am. But here's why I did this. Notice there's 2 pieces here. We have 4 over 6, which reduces to be what? 2/3. And then your plus or minus something. And you can work with that and do what it is, but guess what? That x equal 2/3 is either going to be your minimum or your maximum, because you're going to go up or down on either side of that. That's what the plus or minus tells you. So as soon as you get that minus b over 2a, 4 over 6, you got it. And look in the book, what is your x value of your minimum? 0.67. Who needed a graphing utility? Just a simple little quadratic formula told you that. It told you 2/3, 4, 6. And in the book they had 0.67. Okay? Come on back. All right. Sorry about all the things over the phone. See, this part right here, and then After that, it's plus or minus something, plus or minus something. Okay, so this part right here tells you what your relative maximum or minimum is. Now, you probably can't tell exactly whether it's a maximum or minimum. You'd have to then plug in some other value. 0.67, and all you have to do is take this 2/3 and plug in here. Now that'd be a pain in the neck, but you could do it. 2/3 squared would be, help me, 2/3 squared, 4 ninths, and 3 times 4 ninths is 4/3, right? The 3 cancel into the 9. So that's 4/3 minus, and that would be 8/3. 4/3 minus 8/3 is 4/3 minus 8/3. Negative 4/3, and then minus another 2, which would be 6/3. Okay, so what do we have? Negative 4/3 minus 6/3 is minus 10/3. And they got negative 3.333. Yeah, negative 10/3. So yeah, I think we've run out of time, haven't we? Okay, but we did finish that one. We cheated a little bit, but it's okay. There is a checkpoint. Please do the checkpoint. We will begin next time with average rate of change. Let me give you a few homework exercises because I know you wouldn't want to go home without those. Okay, let me put something in here to hold my place. Some of you are rushing to get out of here. No, look at this. We're almost through the section. You can do either 7 or 9. They're both at Calc Chat. 9's at Calc View. Do either 11 or 13. They're both at Calc Chat. 11's at Calc View. Do any of the odds, 15 to 25. They're all at Calc Chat. 25's at Calc View. Do any of the odds, 27 to 31. They're all at Calc Chat. Do any of the odds 33 to 39. They're all at Calc Chat. 35's at Calc View. I think you can do any of the odds 41 to 47. They're all at Calc Chat. And you can probably estimate or approximate relative minimum or maximum. That's what we're just doing. 49 to 53. They're all at Calc Chat. 51's at Calc View. 55 through 59 are similar to what that is. So try to do those. They're all at Calc Chat. 57's at Calc View. Stop there. We'll pick up with average rate of change next time. Okay. So that's through 59. Good deal. Sorry about the flashing screen. All right. And we'll see you on Thursday. I'm sorry? Page? Oh, I didn't get you when you came in?
No, what page?
Oh, what page? That's page 56, 57. Yeah. Okay.
It's my research.
All right, excellent. Thank you. All right.
I'll fall asleep over here. Wait, is it 2,040 over 3? Because that would make more sense. Well, we gotta go through the quiz. Did you forget about that? No, I should make it one of those. I forgot about that. What do y'all have? That's what I was what do y'all have right in the hall? Who's the teacher? Miss Howard.
She's good. I had her for Psych 210.
Volleyball?
Thank you. Yes.
Yeah. All right.
She is.
Good deal.
I wanted to ask about the topic first before
Okay.
I turn it in.
Okay.
It is a children's application.
Sure.
It's all now. That'd be fine.
That'd be fine.
That's what I need.
Okay. Good deal.
Research paper.
Oh, look at this. A paper already. Excellent. Thank you.
Do we have a quiz yet?
I'm sorry?
Do we have a quiz yet?
Not yet. We'll have at the end of 1.6, and we're almost through 1.5.
All right.
So come up, if not Thursday, next week.
All right.